All right, it's time for another Physics Teachers Are Awesome reaction video. Today it looks like we have, let's see here.
Hello and welcome to...
There we go. Now we can see the mouse. Rotational dynamics and moment of inertia, so that's exciting. It says college physics 1. Often college physics means algebra-based. It's kind of weird, right? Because you could teach calculus-based physics in college, but typically that's the naming convention, is this means algebra-based. And so lecture 25, I think this is from this semester, or this term. That probably started in August or September or something. So here we are at rotation. So let's get going. Looks like there's some chapters here. Example 1, common shapes, rotational dynamics, example 2. So we might jump to the examples after we hear the beginning here.
College Physics 1, Lecture 25, Rotational Dynamics and Moment of Inertia. So up until this point, we've been introducing all these different rotational quantities, that being rotational quantities of position, velocity, and acceleration. So we were looking at angular position, angular velocity, angular acceleration. And then in the last lecture, we looked at the angular equivalent of force, which is torque. What we're really doing here is slowly building toward making a Newton's second law equation for rotation.
Cool.
So instead of F equals ma, something else.
I really like sort of that reminder of where they've been, talking about how, look, we've been looking at how things spin, what it means to spin, what it means to rotate, how we would measure it. And it sounds like then they said, well, how could you cause it? And that's the torque stuff. And then this one, it sounds like it's really about, like, could you predict what would happen, right? So what determines how that cause leads to an effect? Like, by how much would something rotate? And that's really what the moment of inertia is all about. Very cool. And I love, of course, this analogy to Newton's second law. Think about it the same way, right? That you study how things move, what it means to describe motion, how you measure it, how you might cause it, and then how you might predict how that cause could lead to an effect. So F equals ma. Very cool.
And we're actually pretty close to being able to do that. At this point, we have developed enough equations to write an equation for torque based on angular acceleration. The equation here is given: torque tau is equal to the angular acceleration alpha times mr squared. Again, there is a direct correlation between force and torque. Torque is the rotational equivalent. So remember, just like force is a push or a pull, torque is a twist or a turn. If you apply a force to an object, F,
Writing right on it.
you
Very nice.
cause that object to accelerate. F equals ma. Well, if you apply a torque to an object, you cause it to rotate. Same general idea. So to see where this equation that I've written comes from, let's take a look at our definition of torque from our previous lecture. Torque is given by Rf sine of phi. Now, in this case, we're going to be looking at the tangential component of this acceleration. So when we say sine of phi, we're going to be talking about a 90-degree angle in this case. So sine of 90 is just 1. So
Nice.
this is really just R times F for this example. So we have torque equals Rf, but we know from Newton's second law that force is ma. So really we have Rma. But from 2 lectures ago, we saw that tangential acceleration, A, is given by alpha times r. So this equation becomes r times m, and then times alpha r.
Nice.
So this is where that equation comes from. You can see here, if you just do a little rearranging, notice that there's 2 r's. This is alpha m r squared. So that's
Nice.
where this equation is coming from. I don't make my students derive equations in my basic physics class like this, but it's important to sometimes see where the equations come from. We have combined 3 equations: the equation for torque, Newton's second law, F equals ma, and then the comparison between angular acceleration and regular acceleration.
Nice.
namely A.
I really like how he's really driving home the work that they have done before. Look, you've seen this all before. We're just kind of slapping it together here. And also sort of driving at the goal, which is to understand, hey, we've done a whole bunch of F equals MA work. So we're really doing very similar things. And of course, we know that this here is going to turn into the moment of inertia, certainly for a more complicated object. So we're getting there. It's interesting that to prep that, you could contemplate putting the mr squared in front and almost like putting parentheses around it so that there'd be something times alpha in the same way that you have F equals ma, which is right up here. But, as he said, he doesn't, in this particular class, doesn't want students to have to worry about how we got there. He just really wants to have them have a sort of a gut instinct as to where why these variables are in there at all. So the r squared, comes about for two interesting reasons, right? One of the r's is here, and then one of the r's is here. It seems like we add an r to all the stuff we've ever done, but the problem is to get to tau, to get to torque, we've done it twice. We did it on sort of the definition of sort of lever arms, and we did it again when we said, well, this doesn't have units of meters in it at all. So if you want to know how a thing is actually accelerating, you have to scale it by r. So you get two r's, and that's why it's r squared.
Equals alpha r. Anyways, so we have an equation here, torque equals alpha mr squared. Now, in many situations, we're going to have a rigid object, a large object, with perhaps multiple forces acting on the object, each producing a torque. So we would have to find the net torque, the total torque acting on the object. Like you can see in the picture there on the right, there are three forces acting on the object, each of them causing a rotation, in other words, a torque. So if we were to try to solve for the net torque, we add them up, right? You add up each individual torque produced by those three individual forces. Well, using the equation above, each individual torque is given by alpha mr squared.
What's a little bit of a struggle here is, it's drawn as a cartoon, right? And it almost seems like there's some mass in here. And so is this really just a massless substrate that has three masses on it? Because, the indication seems to suggest that every mass has an attached force, right? And so when we think about a thing where the mass is distributed, well, the attachment point of the force might still only be at one place, but it's actually sort of affecting everybody. But I get where he's going here, right? He's like, look, the net amount of twisting that you're put on there is this really cool sum, and so this starts to be the really, really interesting thing. So I just think that this particular cartoon is sort of an interesting way to think about it. I mean, actually, this makes perfect sense if you talk about this thing being mass-free. Or that every single particle on here which has a mass has an attached force, and you just need to figure out everybody's contribution. The important thing is, of course, they all share the same alpha, which is why you're able to factor this out, which is kind of the whole gigantic big deal here. So everybody's rotating the same. There's no interparticle motion going on. They're all just rotating. So bam, you can factor this out. All right, I'm just going to jump to an example. Is this where I want to go? I think I'm more interested in this example. So let's jump to rotational dynamics. All right, let's read it here. Pull, sticks out, determine the angular acceleration as it falls. Oh, that's a cool problem.
Determine the angular acceleration, in other words, alpha. I'll even write that, alpha equals question mark. That's what we're looking to get as it falls to the ground. So step one says to identify the axis of rotation. Well, this object is going to be rotating about the point where it's connected to the ground, right? So this down here is our axis of rotation.
Cool.
We also call that the pivot. So I drew a simplified version of this, or sketched a simplified version of it over on the right here. I exaggerated the angle as well, just so we have some space in our picture to work with. So there's our pole sticking out of the ground, and then step two of our problem-solving strategy, if we reference it, we identified the axis, so we were done there. We know it's rotating.
Oh, I like how he's going back and forth to the scaffold.
So now let's look at the force that's causing it to rotate. Well, the force that is pulling on this pole is its weight, right? It is gravity
I'm just going to pause and just let you know about something I'm going to really watch for, because I think it's tricky, right? So when we say find that second step or third step was find the forces and the distance at which they're acting, we know that this gravitational force is going to be the big deal here, right? But the students also know, because we've just totally pushed it into them over months. There's another force down here. Oh, you can't see. My face is in the way. Let me move my face. Whoa. There, let's move my face over here. There we go. This force is here. Oops, this force is here.
acting on the object.
There. Now you can see. But there's this other force down over here. And this normal force, if you ask a student what might make this thing rotate about its center of mass, you might think, oh, well, this force is pushing it up. It's making it rotate counterclockwise. And so we know that in this problem, this force is not going to show up at all, right? It's really just going to be this one. So I'm really curious to see how he reminds students that there is this other force, but its distance from the pivot point is 0, so we're not going to care about it. It's really fascinating, right? Because suddenly these problems, you don't have to worry about it. In fact, if picking the right pivot point, if it's choosable, lets you get rid of a whole bunch of forces. So I think that's actually a really interesting piece of this. Let's watch how he does that.
So it's the weight of the object pulling down on it, causing it to rotate. So the force that is causing this object to rotate is its weight. I'm going to just label it as F. That's the force pulling on the object, but it is its weight. And then it says to also identify the distance from the axis. So how far away from the axis is this force acting? Well, recall our last...
So just really quick, did you hear what he was talking about? He said, what is the force that's making this fall? What is the force that's making this action happen? So that's the force that he's focusing on. This other force that's down here in this corner, right, is just doing its job to make sure that the thing just doesn't fall straight, right? Because if you put a bar at this angle in air, right, well, I was going to say in free space, but where there's gravity, in a gravitational field, and just let it go, it'll fall and not rotate. Right? So what's causing the rotation is this force, because that's what he's about to calculate. But this is just doing its job of just holding it there.
Lecture. In our last lecture, we introduced the concept of center of gravity. This is a uniform object. So the weight of this object should be acting right at the center. Right? This is our center of gravity.
Super important.
COG, we'll call it. So the force should be acting at the center of gravity, right in the middle. Which means if we want to know how far away this is from the axis of rotation, that's just half of the length. So R is half the length, which is 2.95 meters. Okay, so we know what the distance R is. It's half of 5.9. All we have to really make sure we understand as well is what the angle phi is. We're told that it's the pole is sticking out of the ground 25 degrees from the vertical. Well, this force given by the red arrow is vertical. So this here is our angle phi, the angle between the radial line and your force.
That's tricky because 25 degrees is described in the problem as this angle, right, from vertical to here, right? And so then this being the same angle, this is just, some facts we know from geometry. So it's tricky. And then so this statement here, since weight is a vertical force, the angle is indeed the 25 degrees given. I think there's lots and lots of ways you can do that. You can super carefully figure out what your definition of phi is. One of the things that I like to do is to say, well, as the angle gets, we know it's going to be sine or cosine of 25 degrees. We know it, right? We're so used to doing these problems, it's either going to be the sine or cosine of 25 degrees. Another way to say that is it's either going to be the sine of 25 degrees or it's going to be the sine of 65 degrees, right? That's the same thing. So what I like to do is I ask students, I say, well, if this angle were to get smaller, would we expect more or less torque, right? And so they might sit there and think about, oh, well, my gosh, I'll just take it as small as I possibly can. Let's go to 0. Oh, at 0, there's no torque. Okay, well, then do you want the sine of the function, sine of 25 or cosine of 25? And they say, well, let's see, if I plug in a 0, I want it to give 0. Oh, that's sine. That's a great way to do it, right? To say, let's just figure out, does it get bigger with the angle or does it get smaller with the angle? And that'll tell you which one to plunk into your calculator. All right, taking a look at the time, realizing it got a little bit long today. So I really thought this was a really great setup. I thought that, first of all, really cool how he's changing his colors, and interesting that the students can really, really see when he's switching to an eraser. I think there's something valuable to that. Think about how a chalkboard works. So you absolutely can see when the professor is reaching for an eraser. I actually think that's sort of cool. And on my system, I just have to press a different button on my pen, and boom, it starts erasing. So students would never know that I'm about to start doing that. So I think that's fascinating. And I really liked how he was pulling together so much of the knowledge that they had from previous lectures, including the center of gravity stuff here. All right, everybody. I hope you have a great day. And remember, physics teachers are awesome.